welcome to Keeping Tabs on Chemistry. In this video, we are going to be discussing intermolecular forces. So, intermolecular forces, which are also sometimes called attractive forces, are the attractions that occur between molecules. Now, we commonly abbreviate intermolecular forces as IMFs because intermolecular forces is a bit of a mouthful. But if we actually look at the word and break it apart, intermolecular forces. The prefix inter means between, and molecular is referring to molecules. So intermolecular forces are the forces that occur between molecules. Now, we've spent almost the entire year looking at the forces within molecules. Those intramolecular forces are bonds. So we're no longer looking at what's holding the molecule together, but how molecules are interacting with each other. So IMFs are based on electrostatic attraction between a positive and a negative dipole. It's that opposites attract. So IMFs are not bonds, right? They are actually much weaker than bonds. There are three types of intermolecular forces of varying strength. There are London dispersion forces, dipole-dipole forces, and finally hydrogen bonds. And yes, the name hydrogen bonds is a misnomer. It is not a real bond. But we didn't discover that until much later. So the strength of these forces, London dispersion are the weakest, hydrogen bonds are the strongest, dipole-dipoles are in the middle. So we're going to look at each of these types of intermolecular forces and what kind of molecules experience them. So the first and weakest type, London dispersion forces, these are also sometimes called van der Waals forces. These are named after the people that discovered them, not after the actual city in England, but London dispersion forces are van der Waals forces. These are forces that occur between all atoms and molecules due to the random motion of electrons. When we studied quantum mechanics, we learned that electrons are constantly moving around the atom in this cloud of electrons, and Heisenberg told us, well, we don't actually have a way of knowing where those electrons are at any given point in time. So all electron clouds may create what's called an instantaneous dipole at any given moment. The idea is if electrons are circling around the atom at random, just by chance at any point in time, one side of the atom could end up having more electrons than the other side. This creates a charge difference, right? Electrons are negative, so the side with more ends up having a more negative charge than the other side. So why would it be an instantaneous dipole? Well, remember, those electrons are moving at very close to the speed of light. So as soon as this uneven distribution occurs, it can be gone again. Or it could be on the other side. So it's a very, very quick split moment instantaneous dipole. So dispersion forces are the weakest intermolecular forces because of that amount of time that they can be present. Yes, instantaneous dipoles of two neighboring molecules can have an attraction, but because they're so fleeting, so quick, as soon as they form, they're gone again. So it's an extremely weak force. Now, dipole-dipole forces are the same concept, but with a different electrostatic difference. So, dipole-dipole forces occur only between polar molecules by aligning the positive and negative ends of permanent dipoles. So, permanent versus instantaneous dipoles. An instantaneous dipole is based on the random motion of electrons, which means any molecule can do that. A permanent dipole requires a polar molecule, one that has two elements with an electronegativity difference. Remember, electronegativity is the ability to gain electrons. So looking at the difference between HCl, chlorine has a much higher electronegativity than hydrogen does. So chlorine ends up pulling more of the electrons towards itself, leaving hydrogen kind of high and dry with that slightly positive. We studied this when we looked at the polarity of molecules. So a permanent dipole is always present instead of disappearing like an instantaneous dipole. This means that dipole-dipole forces are going to be slightly stronger than London dispersion forces because they're not fleeting. They stick around, which lets these molecules form their own kind of structure with each other because they have a defined permanent dipole. Now the final one, hydrogen bonds. The name bond is a complete misnomer. The hydrogen bonds are a very specific type of dipole-dipole bond. It is the attractive force between a hydrogen and the lone pair of a fluorine, oxygen, or nitrogen of an adjacent molecule. So you're looking at a hydrogen on one molecule with the lone pair of a fluorine, oxygen, or nitrogen on an adjacent molecule. Hydrogen bonds are the strongest intermolecular forces. They are approximately 5% of a true covalent bond. Now, that doesn't seem like a lot, but remember, these are not from sharing electrons, right? This is just from, the molecules being close to each other and having charge differences and that electrostatic attraction. So 5% is a lot in the world of intermolecular forces. Which is why we thought, oh, hey, hydrogen bonds are their own type of bond. They're not. They're just an intermolecular force. But the name stuck, so we're kind of stuck with that. So, why this is different than a dipole-dipole force? Notice that it is specifically between the lone pair on a fluorine, oxygen, or nitrogen. Fluorine, oxygen, and nitrogen are the three most electronegative atoms, which means they pull electrons towards them better than any other element on the periodic table. This means that those partial positives and partial negatives in the molecule are going to be the biggest differences. So the biggest difference in the charges means the more those opposites are going to attract to each other. So the way we can remember this, FON, you guys might be a little too young for this, but if you've ever seen ET, ET phone home, FON, phone, yeah, that's the best I got. So, the most famous example of a molecule having hydrogen bonds is water. This is one of the characteristics of water that makes it so crucial for life, is the fact that water forms hydrogen bonds with the hydrogen on one molecule with the lone pairs of the oxygen on a separate molecule. In fact, a water molecule can form up to 5 or 6 hydrogen bonds with adjacent molecules, which is why water expands when it freezes and has all these special things that make life possible. So, hydrogen bonds are very specific between a hydrogen and the lone pair on a fluorine, oxygen, or nitrogen. So now we're going to do a practice identifying the strongest type of intermolecular forces between each. Notice I say the strongest type, not all types, because yes, a single molecule like water can experience all three intermolecular forces, but the hydrogen bonds are the strongest one, so that's the one we're concerned with. So for these three molecules, we're going to look at the type of intermolecular forces between each. Now to do this, we need to look at the structure and decide, is this a polar or a nonpolar molecule? So looking at the first one, HF. Okay. Remember, when you're drawing Lewis structures, you're going to start by counting the total number of electrons. So hydrogen is in column 1, so it has 1 electron. Fluorine's in group 17, so it has 7. So 1 plus 7 means I have 8 total electrons. So I'm going to start by connecting hydrogen and fluorine with a single bond and go to complete octets. Now remember, hydrogen's an exception. Hydrogen prefers a duet rather than an octet, so the 2 electrons in this bond are enough for hydrogen. But fluorine needs 6 more to complete its octet, so I'm going to fill it up with 6 valence electrons, lone pairs, 3 lone pairs. So now I've got 2, 4, 6, 8 electrons. Now looking at this molecule, it is not symmetrical. It has an uneven charge distribution. The hydrogen has less electrons than the fluorine does, so this is a polar molecule. So right off the bat, I'm thinking dipole-dipole. But this is a hydrogen attached to a fluorine. Fluorine is one of those 3 special elements, fluorine, oxygen, nitrogen for a hydrogen bond, and there's a lone pair on that fluorine, which means that these molecules, when they're all grouped together, the hydrogen on one will interact with the lone pairs on the fluorine of another. So the strongest type of bond for HF is a hydrogen bond. So the strongest type of intermolecular force for HF is a hydrogen bond. For the next one, CH4, this is methane. I've got 4 electrons from carbon in group 14, plus 4 hydrogens, so that's 4 times 1. That means 8 total electrons. Now remember, carbon is a special snowflake. It likes to be in the center of all of its Lewis structures. I'm going to surround it with 4 hydrogens and connect them with single bonds. Now each of these hydrogens is happy with its duet, and looking at carbon, it's got 2, 4, 6, 8 electrons around it, meets the total number, this is my structure. This is a symmetrical molecule in all directions, all the same hydrogens. So this means that this is a nonpolar molecule. Now, if it's nonpolar, the only possible intermolecular force it can experience is London dispersion forces, LDFs. Finally, I've got CH3Cl. So I've got 4 electrons from carbon, 3 times 1 for hydrogen, plus the 7 for chlorine. That's 14 electrons. Carbon's in the center. I'll surround it by 3 hydrogens and 1 chlorine, and it does not matter where you put the chlorine. Connect them with single bonds. Now hydrogen is happy with their duets, carbon is happy with 2, 4, 6, 8, but chlorine only has 2 electrons. So I need to give it 3 lone pairs, 6 more electrons to reach 8. So I've got 2, 4, 6, 8, 10, 12, 14 electrons. That meets my minimum. Now looking at this, this is not a symmetrical molecule. It has one atom that is different than the other 3 that are attached to it. So this is not going to be symmetrical. That is a polar molecule. Now, there's no hydrogen attached to an F, O, or N. In fact, there's no F or N in the molecule, which means that the strongest intermolecular force it can experience is simply dipole-dipole forces. Alright, that concludes our lesson on intermolecular forces.